In this video, we are picking up where we left off. Quick recap, in the first quantum machine learning episode, we reviewed the basics of classical machine learning and used XOR as our running example. In the second, we showed how to translate that classical problem into the quantum setting, what changes, what stays the same, and how a quantum model could solve it. In the third, we implemented the whole thing in Qiskit and simulated it. Now in this, likely final video of this series, we scaled beyond 2 inputs. Previously we only had 4 possible bit strings, so 00, 01, 10 and 11, and here we go to longer bit strings. And the key rule is simple for XOR. If a bit string has an even number of ones, the label is 0, and if it has an odd number of ones, then the label is 1. There are 2 ways we can test generalization. Option A, we train on multiple lengths, say n equals 3 up to n equals 10, and aim for a model that can classify any length, even ones it never saw during training, like n20 or n30. Option B, fix a single length, and for example n equals 10, where there are 1024 possible inputs, and train on only a small subset, say 100 out of 1024. The goal is that the model still classifies the remaining 924 unseen bit strings correctly. Put differently, either we learn from a range of lengths and generalize to longer ones, or we learn from a small subset at a fixed length and generalize to all inputs of that same length. In this video, however, we will only implement option A. That means we will focus on generalizing across different bit string lengths. On top of that, I'll use this video to show how to run the experiment on real hardware, not just in simulation. I've already executed the code on an actual quantum device, and I'll walk you through the setup and then present the real backend results, what we observed and how they compare to the simulator. In the first part, I will train the model with bit strings of length n equals 3, which means a total of 8 inputs. We will then see that this can actually generalize up to n equals 8. In other words, we can correctly predict the outputs for all inputs of length n equals 8. And that's already quite impressive. I experimented a bit trying to adjust the architecture to make the whole thing work even better, but this is actually not so easy. You either need more experience with neural networks or with quantum machine learning in general, or simply some practice and time to figure out what works well and what doesn't in order to build a really strong network. I didn't invest a huge amount of time into this, I just wanted to see what could be achieved with a reasonable effort in terms of generalization. And what I managed to do is training on inputs of length equal 3. The model generalizes successfully up to n equals 8. But for n equals 9, however, it no longer works. And interestingly, it doesn't really matter whether I train at n equals 3 or n equals 8. Once we go to n equals 9, the performance breaks down. Before I go into the approach I used to build the architecture, I believe that the way I designed it here is specifically suited to make accurate predictions up to n equals 8. If we want to go beyond n equals 8, we would need a completely new architecture. As I said, I didn't put an enormous amount of work into this. My goal was simply to show how it could work, what can be achieved with a manageable effort, how we can generalize, and what the overall scaling process looks like in order to eventually run this on a quantum computer. And now I walk you through the code, and then I'll explain in more detail what works well and what doesn't. So here's how our network actually works. In our old code we had 2 inputs and therefore always 2 qubits. Now, however, we are training with 3 qubits or more, depending on the case. In my example, I train with 3. Then we want to make predictions for an input of length 8, for example, which means we need 8 qubits. This raises a problem. In our original setup, with 2 inputs, we had 3 parameters, and those parameters depended on the number of inputs. But now we cannot simply let the number of parameters depend on the number of inputs. Why? Because if I train with n equals 3, I build a layer with 3 qubits and 3 different parameters. But if I then try to feed in a bit string with 8 inputs, I suddenly have 5 inputs with no parameters assigned to them. That means we need a new approach, one that is independent of the number of inputs. The first idea I came up with was this. In each layer we create, we must use the same parameter for all our Y gates. For example, with n equals 3, we have 3 inputs, so the first layer has 3 RY gates, and all 3 apply the same parameter. In other words, the same rotation is applied to each qubit. If we then go to n equals 8, we have 8 qubits, each with an RY gate, and again, all of them rotate by the same angle on the Bloch sphere. Of course, the problem here is that with this setup, we only have one parameter per layer, and that is too few for the model to actually learn effectively. So what we need are more parameters, which means we also need more layers. And that's why I expanded the architecture. One layer of RY gates, then entanglement, then another RY layer plus entanglement, and so on. In every layer, we always have as many RY gates as inputs. So if I train with n equals 3, each layer has 3 RY gates, and we train them with one parameter per layer. If I then test with n equals 8, each layer doesn't just have 3 RY gates, but 8, all applying the same trained parameter. This is essentially the approach I came up with. It's the simplest way I could think of to make the architecture independent of the number of inputs, while still having enough parameters for the model to learn properly. Now let's move on to the code explanation. This function is called Variational ansatz shared because the parameters are shared across all qubits. We again create our quantum circuit, this time with n qubits in total. Then we have a for loop that builds the individual layers. The depth defines how many layers there are. And inside each layer we create another loop with RY gates. That means for every layer we add as many RY gates as we have qubits, and we apply the same angle feeder to all of them. After that we add C0 gates just like in the previous video. Now, why do I use reversed here? The reason is that in the last video I always measured qubit 0. What we're doing here is linear entanglement. Qubit 0 as control and qubit 1 as target, and then qubit 1 as control and qubit 2 as target, and so on. And this way information flows from qubit 0 toward the last qubit. But if I did it this way, I would need to measure the last qubit in order to read out the result, whether the number of ones is even or odd. Since I always measured qubit 0 in the last video, I wanted to keep it consistent and also measure qubit 0 here. That's why I reversed the direction of entanglement. The last qubit controls the second to last, then the second to last controls the third to last, and so on, until everything flows back into qubit 0, and in the end we measure qubit 0. So the overall structure of our variational ansatz is this. We build layers. In each layer we apply one RY gate per qubit, all with the same parameter. After that we add linear entanglement, but reversed so that everything flows into qubit 0. And then we move on to the second layer, third layer, and so on. What we also had to change, of course, were the inputs we generate. And you can see that in these functions. We have the function generate all inputs, which takes some n, for example n equals 2, 3, 4, 5, and so on. And then it creates all possible input bit strings. So for n equals 2, it produces 0, 0, 0, 1, 1, 0, and 1, 1. For n equals 3, it produces 0, 0, 0, 0, 0, 1, and so on. Simply all possible inputs. With parity label, we then assign the label for each input. The idea is simple. We just sum up all the bits. For example, we have the bit string 0, 1, 1, then 0 plus 1 plus 1 equals 2, divide by 2, and the remainder is 0, and that remainder gives the label. So in this case, the label is 0. If the input string is 1, 1, 1, then 1 plus 1 plus 1 equals 3, divide by 2, the remainder is 1, and so the label is 1. And that's correct because 1, 1, 1 we have an odd number of 1s, so the output should be 1. And with 0, 1, 1, we have an even number of 1s, so the output should be 0. With generate dataset, we simply combine everything and map the 0s and 1s into -1 and +1, since later we measure in that basis. And really those are the only changes. I modified the variational ansatz, I changed the input generation compared to the code from the last video, and otherwise everything else remained the same. We still measure qubit 0, you can see this here. The training loop and expectation value calculation are also unchanged. And here I train with 1000 steps. The reason is simply that with 1000 steps we consistently reached 100% correct predictions. That's why I needed a bit more training. And as I said, the rest stayed the same. We just defined the depth here and the number of bits we want to train on. We do that here. And the rest of the process remained unchanged, and at the end we just print out the results. Here are the results, which I had already run beforehand, since training with 1000 steps would take a while. And what you see here is the progression of the steps. Next we see the final parameter vector, one parameter for each layer. And then we have the predictions for all 8 possible inputs with 3 bits. You can see that the expectation values are very accurate, almost exactly -1 and +1. As a result, we achieve 100% accuracy and only a very small loss. That's essentially the outcome of the training itself. Alright, now we can test the whole thing for bit strings of different lengths. I set it up to test from n equals 2 up to n equals 9. There's also a simple print statement that just tells us which n values we're testing. After that, we run a for loop that takes every possible input for the given n, passes those inputs through the model, and prints out the results. In the end, we get the accuracy, that is the percentage of all inputs that produce the correct label. From the results, we see that for n equals 2 up to n equals 8, we achieve 100% accuracy. That means for every possible input, the model gives the correct output. Starting at n equals 9, however, the performance drops to around 50%. In practice, this means the output is essentially random. I would also like to point out that this is actually quite remarkable. We only trained on 8 inputs of length 3, yet the model correctly predicts 256 inputs of length 8 with 100% accuracy. At this point, I should also mention that while it's quite impressive that the model is able to learn this, it's of course possible, even though I don't believe it, that I may have made some mistakes, or that in some way the results are hard-coded, or that there are certain architectural properties that more or less force this outcome. I don't think that that's the case. I even had an AI check my code for errors and it didn't find any issues. So the parameters really are being trained to correctly predict these inputs, learning to distinguish between 0 and 1. That being said, this only works with exactly 10 layers. If I try running the model with 9 layers, the performance collapses. If I try 11 or 12 layers, it also collapses. As I mentioned before, it also doesn't help to train with n equals 8 or n equals 7. Once we reach n equals 9, the model simply can't predict correctly anymore, even if I increase the number of layers. So with the way this architecture is currently built, we can't just scale it up by adding more training steps or more layers and expect better results. I haven't figured out exactly why it breaks down at n equals 9. Maybe with 9 layers the network is just too simple, not enough complexity to separate the classes, and with 11 layers maybe it's overfitting and the classification breaks down again. I don't know the exact reason, so if anyone does, feel free to share it in the comments. I'd be very interested. Although I think the code is correct, if there is an error somewhere, please do point it out in the comments. I'm always happy to learn more, and of course I can also make mistakes. Now, what could we change in the architecture? First of all, we need an architecture that is truly independent of the number of inputs. That's crucial. So maybe someone could find an alternative approach instead of the layer-based method I used with one parameter per layer. Another thing we could change is the entanglement. Instead of linear entanglement, we could try all-to-all entanglement, where every qubit is entangled with every other, or star-shaped entanglement. So there are different options. We could also add other types of gates to the RY gates, like RX gates, to have more flexibility on the block sphere. That would be another possibility. We could also vary the layers, maybe not use the same number of gates in every layer. So there are lots of levers we could pull to adjust such a variational network. I tried a few combinations myself. For example, I tested all-to-all entanglement and star entanglement, but they didn't work better than what I currently have. So those are essentially the knobs we can turn. There may be others too. The task is to find the right combination to achieve a better result. It would be fascinating to explore this further. Maybe it's possible to build a network that can correctly predict not just up to n equals 8, but up to n equals 20 or n equals 30. Or even every possible input, if that's even possible. Honestly, I don't know if it is. So now that I've shown how the whole thing works, keep in mind that up to this point we've really only done what we also did in the previous video. We simply calculated the state vector. We didn't simulate what it would actually look like on a real quantum computer. What I want to do next is show the code that doesn't just calculate the result, but actually simulates it, or even runs it on a real quantum computer. It's important to note that the training itself still happens classically on our PC. That means we continue to optimize the parameters locally, just as we've done so far. The difference comes afterward. When it comes to testing the results, we no longer do that classically on our computer. Instead, we send the input circuits to a real quantum computer or a simulator and observe the outputs there. Of course, in this case, it doesn't serve a real practical purpose. We could just as well test everything classically, but it's meant to demonstrate that the workflow actually runs on the real hardware. And honestly, it's also just pretty cool to execute the whole thing on an actual quantum computer. Alright, so now I'll walk through the code, give you an overview, and then dive into the details. First, we need to import a few things. Since we want to run everything both on a simulator and on a real quantum computer, we need the Qiskit libraries that allow us to do that. For the simulator, we use the air simulator. The air simulator provides us with all the variables and properties that a real quantum computer would have. For example, it simulates the noise you would encounter on real hardware. In other words, the air simulator replicates the essential characteristics of an actual quantum computer. Next, we have the backend estimator v2. This acts as an interface between our code and the simulated quantum computer. The backend estimator v2 takes the quantum circuit we want to run and connects it to the simulator. Essentially, it ensures that our circuit is executed on the simulated backend. We then import the Qiskit runtime service along with the runtime estimator v2. The Qiskit runtime service is the platform that allows us to access IBM's quantum computers, which are distributed across the world and can be used via the cloud. To use this, you need to create an IBM cloud account. I'll link it in the video description. And the runtime estimator v2 plays the same role as the backend estimator v2, except that it is used for real quantum hardware rather than for the simulator. Finally, we import Generate Preset Path Manager. This tool ensures that our quantum circuit is optimized and translated into a form that can actually run on the quantum hardware. Not every quantum computer can directly execute every kind of gate. Many gates must first be decomposed into basic gates like X, Y, and Z. The Path Manager handles this translation. At the same time, it optimizes our circuit. You can configure it to improve the results by adding additional operations that don't change the logical output of our circuit, but do improve the performance and accuracy on the real device. In order for my code to know which account it should run from, Qiskit needs access to my IBM Quantum account. That means when I execute the code, Qiskit has to know which account instance the circuits are being submitted from. For that, I provide my ID, which I have stored under instance in a separate text file. I simply call it here with a short code snippet using with open. This is not meant to be a tutorial on how to sign up for the IBM Quantum platform or how to log in and use it. For that, I've added links in the video description and one link to the website where you can register and another link to a tutorial that walks through the process. So if you're interested in that part, just check the description. Next, I defined a flag called useRealBackend. With this, you can decide whether you want to use the simulator or the real quantum device. If it's set to false, it uses the simulator, and otherwise it uses the actual backend. Then I added a new function called batch predict expectation all n. So this function here. What this function does is essentially prepare the circuits, submit them to the quantum computer, run them, and return an array with all the measured expectation values. Apart from this one function that I added, which doesn't affect the training since it's only called later during testing, nothing else in the code has changed. The rest of the code, including the entire training process, remains exactly the same. Now let me explain how the batch predict function works. First, we pass a variable called allXTest. This contains all the inputs we want to test. More precisely, for each n, we have an array. So for n equals 2, there is one array with all the corresponding inputs. For n equals 3, there is another array, and so on. Then next we have all n, and all n is simply an array that stores all the values of n, like 2, 3, 4, and so on. Then we pass feeder, which in practice is feeder star, our optimized parameter vector, and after that we have depth, which is just the circuit depth. Now we get to the quantum specific parts. Quantum computers still work with probabilities. Even if we design our circuit so that the probability of getting the correct output is very high, there is always some chance we get the wrong outcome. And once we add noise effects from real quantum hardware, the probability of error becomes even higher. That's why we need shots. Shots mean we repeat the experiment many times to get a reliable estimate of the true outcome. For example, if we have a 60-40 probability split, 60% for output 1 and 40% for output 0, and we only test a few times, it could easily happen that we get only zeros just by bad luck. But if we repeat enough times, we can be confident that the result is indeed 1, as expected. And that brings us to the last variable, the resilience level. This setting tells Qiskit how much it should actively compensate for noise. If we set it to 0, our circuit is hit by the full effect of the noise, and the measured expectation value can differ significantly from the theoretical one. If we set the resilience level to 1, Qiskit inserts extra operations into the circuit to reduce noise effects. These don't change the logical outcome of our circuit, but make the results more stable and closer to the ideal expectation value. There are 4 options: 0, 1, 2, and 3. In my case, I chose level 1. The higher the level, the more extra operations are added, which makes the circuits larger and the execution slower, and more expensive. Since you only get about 10 free minutes per month on IBM Quantum hardware, I didn't try higher levels. Level 1 already worked well, though maybe level 0 would have worked too. I simply didn't test it. We create an array for all the inputs we want to process. For each input we need a separate circuit, and that circuit has to be passed along. We build all these circuits and then store them in this array. We do the same for the corresponding observables. Now looking at the for loop. I won't go through every line of code in detail, but here's the idea. In this loop, we go through each input, build the corresponding circuit, and store it in the all circuits array. And then we do the same for the observables. We also add a small print statement to show how many inputs we are actually passing along. we do that here. PUB stands for Primitive Unified Blocks. This basically means the input block that we send to the quantum computer. And then, at this point, we already decide whether to run everything on a real quantum computer or on the simulator. So if we want to run everything on a real quantum computer, this if condition evaluates to true, and we enter this block of code. What we do here is call service equals Qiskit runtime service, and this tells Qiskit that we want to access the Qiskit runtime to execute circuits on real quantum hardware. This code is simply the standard way IBM defines how to connect to their platform. The instance argument specifies which account ID to use. In my case, it's my own instance ID. That way, Qiskit knows which account to associate with the execution. Next, we define the backend. I chose IBM Torino. On the free plan, you don't have much choice, and this one was available. Based on the name, I assume it's located in Turin in Italy. Then we call generate preset path manager. As I explained earlier, this optimizes our circuit and translates it into the form that the quantum hardware can actually execute. You can think of it like a compiler in classical programming, just as source code is translated into zeros and ones. Here the circuit is translated into the gate set that the specific quantum computer supports. One example of what happens here: not every qubit in the device is physically connected to every other qubit. If we want to apply a C0 between qubit 0 and qubit 3, but those two are not connected in the hardware, then it can't be applied directly. The path manager solves this by remapping and routing the circuit so that the C0 is implemented using qubits that are connected. Once that's done, we actually run the optimization with PM run on all our circuits. The resulting optimized circuits are stored in all Ether circuits. These are the versions we can actually execute on the quantum computer. But since the qubits may have been remapped during optimization, our observables also have to be adjusted. For example, if we originally wanted to measure qubit 0, after remapping that logical qubit might no longer correspond to the same physical qubit. So we need to realign our observables accordingly, and that's what the next line of code does. This line here. After that, we execute everything. We define the backend, the resilience level, and the number of shots, and then bundle everything, the circuits and the observables, into a single array. This array is submitted as one job to Qiskit runtime, which then runs it on a quantum computer. And if we don't want to run it on a real quantum computer, but instead on a simulator, then the else condition is true and this block of code is executed. It basically does the same thing I just explained, only adapted to the simulator. After that, regardless of whether it was run on a simulator or on the real quantum computer, we package everything into this array and return it. And that's basically what the function does. So now we can go ahead and train the model. I've already done that here. It's exactly the same process I showed earlier, trained in the same way as in the previous code, where we only calculated the results. Nothing else has changed. Again, it was just calculated. If we move on, we get to the code that actually executes everything, either on the simulator or on the quantum computer. Just like in the previously discussed code, we can set a minimum and a maximum range. Now we also need to define the shots, how many times each test is run. Here I set it to 1000 and the resilience level is set to 1. This might be redundant since I had already defined it earlier in the code, but it doesn't really matter as long as we use the same values consistently. Then we have a few print statements just to give us some information, and after that we build all N, all X test and all Y test. The for loop simply fills these arrays, all x tests with the input values and all y tests with the labels. Afterward, we call the batch predict expection function that we just discussed and store all the resulting expection values in all y exp. After we've gathered all the data and the execution has finished, we also want to output the results. For that, we use another for loop that checks whether our data matches or not. In this loop, we verify if the expection value, the value actually returned by the quantum computer or the simulator, agrees with our label. We then print the results. Specifically, for every n, we check all the inputs and also display how many inputs we tested. In this code, I set it up so that we test all possible inputs for each n. We then output the total number of tests per n along with the accuracy. That is, the percentage of predictions that were correct. After that, we have another for loop, and all it does is print each input together with its corresponding expection value. Then it outputs whether this corresponds to 0 or 1, what the correct label should have been, and finally marks it in green if it matches or in red if it doesn't. Here we are using the simulator, not the real quantum computer. I've already tested it on the real hardware off-screen and saved the results in an Excel file, which I'll show in a moment. But what you see here is the simulator. At the top, we set use real backend to false, which means the simulator is being used. The training was done exactly as I explained earlier, just like in the previous code. And now I tested it with 1000 shots and a resilience level of 1. The results are, for n equals 2, 3, 4, 5, 6 and 7, 100% of all inputs gave the correct output. For n equals 8, we still had 98.8% accuracy, so about 2 cases were wrong. If we look more closely, we can also see the individual inputs and their expection values. For n equals 2, the expection values are exactly -1 and +1. For larger n, the values degrade somewhat. For example, at n equals 5, we already see expection values significantly below 1, sometimes as low as around 0.2. At n equals 6, the fluctuations are even stronger, but everything is still classified correctly. At n equals 8, however, we see the first mistake. One output, for example, has an expection value of 0.02, when it should have been negative. It's barely positive, but that flips the classification. In total, there are about 3 errors at n equals 8. And finally, at n equals 9, we see that about half of the predictions are wrong. At this point, the model no longer makes reliable predictions. So after showing the results on the simulator, let's now look at the outcomes from the real quantum computer. As I said, I ran this off-screen once on real hardware. The entire run took about 52 seconds. I didn't run as many shots as on the simulator. Instead, I submitted a total of 284 inputs. For n equals 2, 3, 4 and 5, I used all possible inputs. Starting from n equals 6, I only used half of the possible inputs for each n. So for n equals 6, 7, 8, only half to save computation time. Each input was executed with 500 shots and the resilience level was set to 1, just like before. The only differences were that I used 500 shots instead of 1000 shots, and I didn't run the full set of inputs for higher n. The result for n equals 3, 4, 5 and 6 is exactly 100%, so every input was predicted correctly. For n equals 7, the accuracy dropped to about 95%, and for n equals 8, it dropped further to around 93%. We can also see this directly in the expection values. On the simulator, we had values close to exactly +1 and -1 for n equals 2. But here on the real quantum device, we have expectation values around 0.7. So clearly the noise in the real hardware was much stronger than in the simulator. If we scroll down, we can see that everything up to n equals 6 was indeed 100% correct. Starting at n equals 7, some errors appeared. And by the way, the reason you don't see certain zeros in the table is just because Excel cut them off during import. For example, here, there should be another 3 zeros. At n equals 8, we had a few more errors, though still not a huge number. This could potentially be improved by raising the resilience level, choosing a higher optimization level, or running with more shots. But of course, all of these options would cost more computation time and resources. I hope this was clear and understandable and that it gave you a good insight into how to use a simulator or a real quantum computer with Qiskit. If you have any questions, feel free to leave them in the comments, and if I made a mistake, please let me know. Mistakes can always happen. I also want to mention that Qiskit has built-in machine learning libraries. I'm not sure if I've mentioned this in other videos, but I didn't use them here because I wanted to build everything from the ground up. Still, these libraries do exist. For example, they allow you to calculate expectation values or even gradients much more easily. I might make a future video where I show how to rebuild this code using the Qiskit machine learning libraries. In fact, I already have some code where I adapted the XOR example to use these libraries. So that could definitely be the topic of an upcoming video. Otherwise, I hope to see you again soon. Until then.